So I'll just write now. Today, what we are going to see is write the full character table for C3V point group, C2V point group, and this will be followed by there are some properties of character table or rules of character table to build a character table. How there are some rules, so that I will list it out. After that, we'll take different motions like translational motion, rotational motion, and then see how the characters, how one can write how the characters can be written. For we take some simple water molecule, and then we can see. If time permit, then we pick up water molecule and then study the vibrational modes of water molecule and its symmetry. Okay, so that's what I have planned it. Let's see how much we can finish. So I'm going to write the full character table for C3V. So it will have G1. Let me write the symmetry elements. So it has two classes, right? So I'm going to write as E as one class, C3 as another class, and 3 times of sigma V. So that's another class. So it will have three, since there are 3 classes, so there will be 3 IRs, and this will be A1, A2, and E. Okay. So A means we said this is 1, 1. Here both are 1, and it has negative in sigma. So this is A1 means all are positive, and A2, this is A2. So A2 means it will have 1 negative in sigma V plane. And E is 2-dimensional IR, so it will start with 2 under E, and this will be again 1 or minus 1. I would say this is minus 1 and 0. So you don't have to memorize. We'll see how we got these numbers. Okay, you'll come to know there are some rules. I'm just writing the full character table for C3V point group. So this is it has another column which tells about the translational and rotational vectors or bases. We can say these are the bases. So A1 corresponds to Z, and this one A2 corresponds to RZ. Okay, and third one is this is X, comma Y, and then Rx, comma Ry. So some books instead of writing just Z, they also write RTZ. They can also write T subscript Z. So this is, as you know, this is the first column is Mulliken symbols of IRs. This I don't have to tell, you know this. And then these are the various characters of this representation. So 2 E means it's a 2-dimensional matrix. That's why it is written. And third one, this part is called as it has translation rotational basis or vectors, you can say. Translational and rotational vectors. So R means it's basically rotational in X and Y axis for Z, and then RZ means in Z axis a rotational vector is given. And last column, there's one more column. Okay, so the last column is I'll just write the details. We'll see when we study the metals. Okay, metal complexes. So this is x square plus y square, comma z square for A1, and there won't be anything here. And the last one is it will have x square minus y square, xy, and last one is the xz, yz. So last column is called as binary products. Okay, you can see, you can make it out from the last column that these are also, you can say, d orbital shapes, right? D z square, d xy, yz, zx, and then it can be zx also, and then d x square minus y square, and then d x square plus y square. Of course, this is not the d orbital, but group theory predicts the shape of the x square plus y square also. So this is called as the binary products. This becomes relevant when we study metal complexes. Okay, but today we will concentrate on mostly on this. We'll try to use this. So this column is called as column containing translation rotational vectors, and these are the characters. Okay, so this is the typical character table for C3V. First time we are reading, right? Okay, so this is character table. We can I can write the rules. Say, for example, there are a set of rules given for character table. One is there are 4 rules. First one is if you square the dimension of the IRs, it should be equal to the H. So H is in a point group. Number of elements present in your point group is called as order. Okay, so I define a word called order. Or symbol is H. Okay, the number of elements present in the point group is called as order. So it could be in C3V. The order is 6. So this is 1 plus 2 plus 3. So it's 6. For C2V, it is 4. The order of the point group is 4 in C2V. So with this definition, there are a set of rules proposed for the character table, which all the character tables obeys. If you see any quantum chemistry book having the group theory part, if you see the last pages, you will find character tables. Multiple character tables will be there for each point group. Okay, it's like a log table you have, no? In school days, you have seen log tables. Similarly, there will be a character table present for each point group. So rule says is to sum it up, all the dimension of IRs, that will be equal to H. So some more all the IR dimension. This is L stands for the dimension of the IR. Okay, so L is the dimension of the IR. Of IR. IR means irreducible representation. So in this case, you can see it is in C3 case it is 1 square plus 1 square plus 2 to 2. So it is 4 plus 5 plus 1, 6. So you get 6 in this case. So this is 1 square, this is 1 square, and this dimension E is dimension of E is 2. So it is 1 square plus 1 square plus 2 square, 6. So H is 6 in this case. C3V is 6. So it is H equal to 6 in this case. Here you have 6 symmetry elements. So that is first rule, and let me go to the second one. Second one is, if I remember correctly, if you take the product of 2 IRs, then it will be equal to 0. Okay. Or why do you? I mean, that is one. Where is this? Or just stick to the IR itself. So I give you a symbol for characters. So characters of I square will be H. So this rule is if you square the characters of each IR, okay, and that again will be equal to H. H is the order of the group. So any IR you take, so say take for A1, okay, so in case of A1 it is 1 square plus 1 square plus 1 square equal to it would be just 3, right? It's not, it should be 3. It's not correct, but it should be, you have to multiply with these two. Okay, the 2, 1, 3 also you have to multiply it. So this is not correct. So you have to do it 1 square plus 2 into 1 square plus 3 into 1 square. Okay, now you get 1 plus 2 plus 3, then you get 6. Okay, that's why I choose this point group. In water, you will not find, in C2V, you will not find this clause. So there are two C3s, right? C3 and C32. That's why I have written 2 times. And sigma V, there are 3. Sigma V prime, double prime, triple prime. So that has to be multiplied along with the characters. When you do that, then you will get 6. So you can choose for E. Let's do it for E, okay? So it was what? 2 square plus minus 1. 2 into minus 1 square plus 3 into 0. Okay, this is nothing. So it's 4 plus 2 equal to 0, equal to 6. So you get sum of squares of each character of the IR is equal to the order of the group. So there is a second rule. Then you can, based on this, people generate the character table also for the complex molecules. So this is the second rule. Third one is if you take the product of 2 IRs and sum it up, then the sum is equal to 0. So basically they are conjugate or orthogonal. Both are orthogonal. A1, A2 are orthogonal. So third one is, so basically what it means is chi I, chi j will be equal to 0. So chi I is say A1 we can say. So A1 into A2. So if you take that, so what will happen? That's a 1 into, this is 1 into 1 plus 2 into 1 into 1 plus 3 into 1 and minus 1. So this one comes out as 1 plus 2 plus 3. So this will become 0. Okay, because A1 and A2 are orthogonal. So if you take the product of A2 IR, then it should result in 0. It just cancels out. Similarly, you can try with A1 into E. Okay, so you should get the same thing. So this is the third rule. If you take the product of 2 IR, then it should be equal to 0. So that's the third one. And last is we already know this is fourth is number of classes equal to number of IRs. Is equal to number of IR. Okay, so here in this C3V molecule we have 3 class E, C3 and sigma V. So then you will have 3 IRs. Here in this case A1, A2 and E. Okay, so these rules are followed for any character table. Okay, so any question in this case so far? I hope you guys are present. See, we could not see you guys, right? So we keep simply seeing the board and monitor. Yes.
Sir, please repeat the rule number 4.
Please repeat rule number 4. Huh? Okay, so rule number 4 is number of classes equal to number of IRs in the character table. So maybe 1 or 2 class back we have seen how to compute the class, right? I think we took the same example, C3V group, and then if you perform similarity transformation, you are always getting same thing, right? Either you get C3 or C32, that is one class, and then if you perform with sigma V as your similarity transformation conjugate element, and then you always get sigma V prime or double prime. So you got 3 classes in the case of C3V point group. So number of classes in a character table is equal to number of IR. So these are IRs. Okay, so you have 3 IRs. Okay, so that's what I was studying. In the case of water, I'm going to write the water molecule now. I mean the C2V point group. In that you will have 4 classes. each element is its own, its class by itself. So you will have 4 IRs in C2V point group. Okay, so this is the rule. So let's write for water molecule or C2V because we are going to use this. Okay, this is C2V. We have E, C2, sigma V prime, and sigma V double prime. If you fix the axis, so this is X. Either way, you can choose Y, Z. So you have 4 class by itself. So there will be 4 IRs. Okay, so A1, A2, B1, and B2. So A1 is simple, all will be positive. And A2 is it's for E, C2 will be negative. And then sigma V will be what? Negative? No, it's fine. I'm sorry. This is positive. This will be, both will be negative. And B1 is the difference between B and A is negative in C2. Okay, and we have to write the other 2. So B1 is 1 and -1. And since it is this way, so this will be -1 and 1. So this is the characters of all the IRs for water, and here this is very important. Here we'll write. So this is for A1 is Z, and A2 is RZ. B1 is XN or Y, and this is B2 is Y and RX. Okay, so this is for the translation rotational vectors. So here this is x square hyphen y square comma z square for A1, xy, zx, and then yz. So this is the binary elements for C2V point group. We are not writing x square plus y square, but this is sufficient because in our chemistry problem we are going to see only d orbital which has 5 orbitals, right? So we'll take this one. So this is for the water. You can say for water molecule, these are the characters. The same rule valids. Valid in this case also. There are 4 classes, so you have 4 elements, 4 IRs, and then if you take A1 and then or you take the dimension of the IR, square it, it will become 1. It will become H. So it's 1 square plus 1 square plus 1 square plus 1 square. So this will become H, order of the group. So H here is how much? 1, 2, 3, 4. So we have 4. That is first rule is valid. Second rule is if you square the characters and sum it up, then it should be equal to H. So you square it, any IR you take, 1 square plus -1 square, -1 square, 1, you sum it up all. So it's going to become again 4. So that rule is also valid. Third rule is if you take the product of any 2 IR, say A1 into A2, multiply it. So what? The 1 into 1 plus 1 into 1 plus, so this will become negative, this will become negative. So this gets cancelled. So you take the product of A1 into A2, that gets cancelled. So they are orthogonal. Similarly, you take other combination, A2 into B1, so it's going to be orthogonal. Okay, so this is the point group for C2V or character table for C2V. And now we'll see. Go for this. Okay. So I was telling you these are the translational vectors or rotational, right? So to find out the vibrational modes, the symmetry of vibrational modes in water molecule, one can apply this table. So let's start with that. Okay, and then see it. So basically, what we have to do is first draw the molecule of water. Station of C2V. Okay, I hope you. Let's follow this. Okay, so water molecule as such has say we take the water molecule. So how many vibrational modes are there in water molecule? Can you tell me how many vibrational modes in water? Yeah, koi bolo. So whoever is awake.
So three.
Huh? Can you repeat?
Three vibrational modes.
So you said 3. Okay. So how we got 3 and minus 6, right? So 3 into 3, 9 minus 6. So we should get 3. So there are 3 vibrational modes. Okay. So total modes is 9, right? So there are 9 modes. In that 6 we are subtracting. 6 are 3 translational, 3 rotational. Okay, so we are going to subtract that and then find 3 vibrational modes. Let's see. Now we take the atom. By atom, we just put axis. So which axis do I put? So you can say either we can put x1, y1, z1, and then again just mark it as a sphere for each atom. So this is y2, z2, and then x2. Okay, I'm erasing this. This is this, and again this I call it as y3, z3, and x3. Okay, so now I have 3 spheres. Each atom has its own Cartesian coordinates. Now we perform these operations. So what we do is we just extend this and then write Betz notation and then write what is the reducible representation. We're going to find the reducible representation. Okay, for each symmetry operation. So if you perform E, the molecule is not going to. The atoms are all remaining as such. You are not changing it. So all the atoms are unchanged. That means vector also remain as such. Okay, so that means it will have 9 vectors. I just write as 9 here. 9 how comes? I mean the x1, x2, x3 is 3, y1, y2, y3 another 3, z1, z2, z3 all are going to be at the same place by symmetry operation E. Okay, that's why I written 9. Now let's do C2 operation for this molecule. If you rotate it clockwise, we just invert it. Y becomes or y1 becomes minus y1, right? And then x1 will become minus x1, and then z will become z1. Z1 will remain as z1, whereas x and y will remain. We'll change it to these two. And in the process, you interchange the atoms. That means this atom comes to, so I call it as HA, HB. So if you rotate it by 180 degrees by C2 operation, these two atoms interchange it. That means Cartesian coordinates have changed. That means it's all completely changed. So this is going to be 0, and only this one is going to happen. So what happens is it's minus 2 plus 1. So this is going to be minus 1. So all others are 0. You can say everything is going to be 0. This is for this is oxygen atom, this is for hydrogen A atom, this is for hydrogen B atom. So for C2 operation, this is just -1. So the reducible representation for C2 is -1. Okay. Now I go for sigma V. To perform sigma V prime. So let's keep the notation. Sigma V prime means bifurcating, I mean dissecting the molecule into two half. You just slicing it, just cut it. It goes into two slices. So sigma V prime. Basically, what we are doing is XZ plane. To do that, if you apply sigma V with XZ plane, happens. So if you place the mirror here, these two will interchange. So I would say 0 plus or 0, I would say, because all atoms interchange. These two are interchanged, so the vectors are all changed. Whereas here, what happens? This is Z1 will remain as Z1 only. X1 will remain as X1. Whereas Y1 will change it to -Y1. Yeah, so this Y will go to other side, left side it will come. If you cut the molecule into two by plane. So place a plane here. The Y1 goes to -Y1, X1 remains as X1, Z1 remains as Z1. So if you add it up, what? 2 positive, 1 negative. So it's +2 -1, so it is going to be +1. Okay, for sigma V prime, so it is +1. Okay, now last one. Let's try with sigma V double prime, which is YZ. So apply YZ plane, what happens? Anybody can guess?
+1.
Yes, tell me, for YZ plane, what you'll get?
+1.
+1,
+3.
+3. Let's see
Reducible presentation, please.
So if you place a mirror on top of this molecule, the atom's position are not going to change. It will remain as such. So let's start with the Z. Z will remain as Z1. Y1 will be Y1. X1 will become -X1. Okay, so this is first case. Here again, Z2 will remain as Z2. Y2 will remain as Y2. And X2 will remain as X1 or X2 becomes X2, -X2. Okay. Because atoms are all not changing it. Last one is again Z3 remain as Z3. Y3 will remain as Y3. And X3 will be -X3. So you have 2 positive, 1 negative. So it is 1, 1, 1. So 3. So add it up, it's all 3. Okay. So it becomes +3. Yes, somebody got it correctly. So this is a reducible representation, having all the characters. So now we have written the reducible representation for water molecule, considering Cartesian coordinates for each atom. Okay. So I erase this part. Now, how do you find out the translation, vibration, right? So for that, what we will do is so how do we write this? 9. So this is a reduction. This is 9 -1, 1, 3, right? After that, we have to use what is called as a reduction formula to get the vibrational modes. So what we do is we use a reduction formula. Let me complete, then you can appreciate it better. So IR, so this is a reduction, right? Reduce 3n into, so this is reduce 3n into IR. So what we have done is we have got this one, gamma R. So what we do is gamma of A1. you want to find out gamma of A1, we multiply with 9 into 1 plus minus 1 into 1 plus 1 into 1 plus 3 into 1. Let's see if I'm doing it correct or not. So this would survive or not. 9 minus 1 plus 1 plus 3. So this gets cancelled 12. This is divided by h. H. So 1 over 4. So it is 1 over h is what? H is 4. So this is 12 by 4. So it's 33. So we use what is called as a reduction formula. So it is given as 1 over h summation over the symmetry elements multiplied by its characters. So chi into I skipped it. That's a problem now. Okay, chi of chi. Huh? So reduction formula is given as 1 over h. Yeah, 1 over h is order. Then sum over I, you can say. And then chi into chi. So chi I is each characters of the IR, and then just chi is it's corresponding the symmetry element. Okay. So here it's all 1 1 1 1 1 1. Okay, that's what I have done it. So you have what? The reduction formula 9 minus 1 1 3, right? So 9 into its character 1 I have multiplied, and then minus 1 plus 1 into 1. So this means third was 1, and then multiplied with 1. So this is I have done it, and then 3 into this is plus 3 into 1. So that's what I'm doing, 3 into 1. So this is 1 over h. H is 4. So I have written 1 over 4. And then if you do it, this A1, it appears 3 times. So I can write this one as 3 times of A1. Okay, similarly, you have to do it for A2, B1, B2. Then you will end up with its characters. So I need a bigger board. So A1 is, so we get 3 times of A1. Okay. So now I erase this and then go to the next part. Let's do the A2. Over 4, 9 into 1 plus minus 1 into 1 again plus 1 into minus 1. So this is 1 into minus 1 plus 3 into minus 1. Okay, so if I evaluate this 1 over 4, 9 minus 1 plus minus 3. Okay, so is it correct? Minus कितना हुआ था? Minus 5. So it is 9 minus 5 by 4. So this is 1. Okay, so I have plus 1 time of A2. Okay. So what I'm trying to do is with all the reduction formula, I'm splitting into various IRs. A1, how many will be there? A2, how many will be there? Okay, so I got 1, A2. Similarly, do it for B1. So again, 1 over 4. B1 is 9 into 1 plus minus 1 into B1 is minus 1. Plus this is minus 1. No, this is what? This is plus 1 into B1 is 1 plus 3 into 3 into B1 is minus 1. So if I evaluate this, 9 minus plus 1 plus 1 minus 3. So 11 minus 3 is 8 by 4. So this will become 2. Okay, so you have 2 B2 plus 2 times of B2 or B1, 2 times of B1. Okay, now let's do the B2 one. B2 1 over 4, 9 into 1, and then minus 1 minus 1. That means by plus then this one plus 1 into minus 1 plus 3 into plus 1. Nine plus 1 minus 1 plus 3. So 9 plus 3, 12. So 12 by 4, it's 3. I got 3. So here it is plus 3 times of B2. So what I've done is the reduction formula. Using reduction formula, the reduction matrix I have reduced to this form. It has 3A1, 1A2, 2B1, 3B2. So this we have done it. A2, B1, 3B2. Okay. So if you see the table, so what we have, so all the symmetry operations. So basically, the water molecule has 3 atoms, so it has 9 degrees of freedom, right? So it has 3 vibrational degrees of freedom, 3 rotational, 3 translational mode of freedom, and out of 9, 3 will be A1 symmetry, 1 will be A2 symmetry, 2 will be B1 symmetry, and 3 will be B2 symmetry. Okay, so it is 9 degrees of freedom. Okay, so I can write. So it's 3A1 plus A2 plus 2 times of B1 and 3 times of B2. So out of that, I remove the translational vibrational. So I write translational plus rotational. So that I can see from this table and write. So this is this column is translational and rotational, right? So Z corresponds to A1, okay, and XY. So it's B1, B2 plus B2 or translational. Okay, X stands for B1 and Y is B2. So that's what I've written here. A1, B1 plus B2. This is translational. Rotational is you can see it is A2. Rotational is A2 plus B1 and B2. B1 is RY and B2 is RX. So B1 is RY and B2 is RX. So okay, translation rotational is something like this. I can sum it up. So it is A1 plus A2 plus 2B1 plus 2B2. So these are symmetry elements for elements for translation rotational. Now we have total. Total we got it by reduction formula. So this is total and this is for translational rotational. If you subtract this, you will get vibrational, right? So gamma of vibrational is you can strike it out. So 1A1. So this goes to A2 gets cancelled. B1, this one gets cancelled. This one too, so this one gets cancelled. So what is remaining is 2A1 and B2. So you will have 2 A1 symmetry and 1 B2 symmetry in vibrational mode of water molecule or any point group having C2V. So any molecule having C2V point group. So we consider water molecule. For that, you also told me there will be 3 vibrational modes of freedom, right? There are vibrational modes. Chemists know, right? There are, it's called as symmetric stretch, asymmetric stretch, and bending mode, right? So it has three. So we can write that three here. So doing water molecule, so you have a symmetric stretch. Yeah, this will go up, this will stretch downwards, this will come, or the vice versa. So this is symmetric stretch, and then there is another mode. So this is A1 symmetry. This will have A1 symmetry. Okay, because we are getting two A1s. So one symmetric stretch is A1, bending mode. Let's then go to the next one. Bending mode of water. Okay, so for bending mode, what? So again, what this angle is going to reduce, right? So these two will come together. Something like this. So this is by represents something like this. So the angle will go up and come down, go up and come down. So this angle will change. So that's a bending mode. When it happens, this is having again A1 symmetry. The symmetry will not change in bending mode. All the angle will change, the symmetry will not change. So this will also have A1 symmetry. And third is asymmetric stretch. So you take the water molecule, H. So this will go this side, this will stretch this side, and then this hydrogen will go towards oxygen. So you know the graphics, I guess. So this hydrogen, the OH bond stretches, this OH bond reduces its distance, whereas the oxygen, so this is shown by this. So this asymmetric stretch, and this will have B2 symmetry. So for this orientation, it will follow all B2. B2 is for E it is 1, for C2 it is -1, for sigma V prime it is -1, again sigma V double prime, again it is +1. Okay, so what we have done is we had a C2V group table, character table, and then we took the water molecule, which is a C2V point group. In the C2V, in the water molecule, there are 3 atoms, and for each atom we consider the Cartesian coordinate and wrote the reducible representation, reducible characters for that modes, and then we use the reduction formula and got the what are the symmetry elements present in that form. So we got so many things: 3a plus 1 plus 2b plus 3b. 2. Okay, so if you count it, 3 plus 1, 4, 4 plus 2, 6, 6 plus 3, 9. So you get 9 symmetries. So in water molecule, there are 9 degrees of freedom. No? So each one will have its own symmetry. And from the character table, we found out translational and rotational. Translational is A1 plus B1 plus B2. And rotational is A2 plus B1 plus B2. So to find out the vibrational, we subtracted it. We subtracted the translation rotational from the total. So once then we subtracted, we got 2A1 plus B2. And then, as you know, water has 3 modes of vibration. They are symmetric stretch, asymmetric stretch, and bending. So symmetric stretch and bending have A1 symmetry, and asymmetric stretch will have B2 symmetry. So this is what we got. Okay, any question? If not, you work it out for in next class. You work it out for some other molecule. Let me see. C3V. For ammonia molecule, you try it. Okay, you let me know the vibrational frequencies, vibrational modes. What are the symmetries of ammonia molecule, which is having C3V point group? Okay, so this is straightforward. It's a lengthy process, but yes, you can do it. Further, you need the point group, which I already given. Character table, you need it. For ammonia, for C3V, I already given. So you work it out for ammonia. Symmetries of vibrational modes. So ammonia, right? 4 atoms are there. 4 into 3, 12 minus 6, 9. So that should be 9. I think 9 vibrational modes. How many will be there? No.
So 6 vibrational modes.
9 degrees of freedom. Then you have to subtract 6, so you get 3 into 4. Sorry, 12 minus 6. Sorry, 6 you should get, right? 6, correct? No. So 3n minus 6. Ammonia, कितना vibrational modes है? I lost track.
Sir, 6 vibrational modes will be there.
Yeah, 6. So you should get 6. So 6 you will get. So we find out all 6. I've given the point group, right? I've given the point group. Then you draw the molecule ammonia for each atom. You write the Cartesian coordinates, or you can take the bonds and then also you can do it. You work it out. Okay. If you have a problem, you can do it again. Yeah. Fine.